Hello again. As we already know how the BFS or breadth first search and DFS or depth first search work, I wanted to discuss what type of question you should expect in the exam. So in the exam, I will not ask you to write down the algorithm shown here. You should be familiar with this algorithm and you should be able to do the simulation using this algorithm on some graph. In this video, what I'm going to do, go through a simulation of the algorithm here in a graph. So let's talk about what the algorithm does. At the first line, it marks all the vertices unmarked. How you can do that? You can create an array. Let's say this is our graph. First step of our algorithm in the line 1 is mark all the vertices unvisited. So what can we do? We can create an array of size 4 here. We will keep track of whether we visited the vertex or not in this array. So this will keep track of whether A is visited or not, B is visited or not, C is visited or not, D is visited or not. At the beginning, none of the vertices are visited, so everything is false. Next, we initialize an empty queue. So we'll keep track of a queue here. What is the job of this queue? This queue will keep track of which vertex to visit next. In this line, line 3, we have a for loop that will go through each vertex in the V. If the vertex is not visited, then we will visit the vertex V. So what does it mean by visiting the vertex V? We will change the status of the vertex here in this array, and also we'll keep track of some variable called time when the vertex was actually visited. In our graph in this diagram, we start from vertex A. So A is not visited. What we do? We visit A. That means we make this one true. Then what we do? We enqueue the vertex A into the queue. Then we go to the next step of our algorithm. The next step is algorithm 2. What it does at the beginning, it checks whether the queue is empty or not. In our case, the queue is not empty. It has one entry, which is A. So we take that entry into another variable called V. So at this time, V is A. Then what we do in the line 3, we have a for loop. We go through all the adjacent vertex of the vertex V. In this case, A. So what are the adjacent vertex of A? The adjacent vertex of A are B and C. One thing to remember here is you always discover all the adjacent vertex in alphabetical order, not in random order. So you should remember this one for the exam also. I will ask you to do the simulation when you have discovered something in the adjacency list. You always discover the vertex in the alphabetical order. So this for loop will go through all the adjacent vertex. What are the adjacent vertex in this case? Adjacent vertex are B and C. At the beginning, we'll start with B. That means W should be B. We looked into the array whether B is unvisited or not visited. We can see the vertex B is unvisited. So we visit the vertex B. That means we change here. And we also keep track of the time. That means at the beginning when we started, the time for A was 0. and when we visit A, we incremented the time by 1. So for B, time will be 2. For now, let's forget about the line 6. We'll talk about line 6 later. So what the next step? Next step is we add the vertex W to the queue. So we already dequeued A in line 2. Now we are adding B to the queue. So now we have ended the if, then we will end the for loop and we will go back to the for loop again because we have not processed all the adjacent vertex of A. Next, W will be here, that means C. At this time, what we do? We check whether C is visited or not. If we take a look at the array, again, C is not visited. So we can make it visited by visit W. And for C, the time will be 3. Again, we will add C to the queue. We end the if, we end the for, we end the while. Then we go back to the beginning of the while. While loop check whether queue is empty or not. Queue is not empty. So what we do? We again dequeue the first node or first entry in the queue. So we dequeue B. That means V equals B. Next, we look all the adjacent node of B. At this time, when we look at the adjacent node, we see the adjacent nodes are C and D. But when we check C, it is already visited. So we will not go through C and D in this loop. We will also only go through D. At this point, what we do? We look for what are the adjacent vertex of B. The adjacent vertex of B are C and D. C and D. So we will go through this for loop again with C. At the beginning, W will be C. But when we check whether C is already visited or not, we see C is already visited. So we will not go through the if clause. We will end if and we will go back to the beginning of the for loop. W will be here. At this time, what we will do? We will visit W. What does it mean by visit W? We will, what is W here? W is D. So we will change the status here and then we will keep track of the time for W, which is 4. Previously, time was 3. You can think of time as a global variable. We are incrementing every time when we visit a new vertex. We visit D and then we enqueue D in the queue. So we end the if, we end the for, we go back for the for loop. There is no other adjacent vertex for B, so we end the for loop there. Then we go back of the while loop again. We take a look at what the queue holds at this time. At this time, when we enqueue the queue, it will be C. That means V equals C. At this time, again, when we check the adjacent vertex of C, we see adjacent vertex are A and B. So we came back again in this for loop, which will go through all the adjacent vertex. W will be here, but when we check whether the W or the vertex adjacent to C is discovered or unvisited, we see here the vertex is already visited. So we will not do anything with A. W will be here. Similarly, when we check the array here, we see the vertex is already visited. So we will not do anything here. So when we did this, we actually include C at the beginning. So we are done with the for loop. Again, we will go back to the beginning of the queue. We see queue is not empty. At this time, V should be D because we dequeue the entry from the queue at the beginning of the while loop. What are the adjacent vertex of D? The adjacent vertex of D is only one vertex B. So we will go through the for loop in the line 3 again. B would be W, but B is already visited as from the array. So we will not do anything else. At this time, we have not added anything, but we can see the queue is also empty. So this while loop will end. With this while loop ending, the algorithm 2 will finish its processing. We will go back here in the line 7. We will end if and then we will end for. Next, we will go back at the beginning of the for loop. At this time, what we have done actually, we started this for loop with vertex A. So we have not checked all the other vertex. What are the other vertex? B, C, and D. So we have finished this for loop for vertex A. Next, we will check and go through everything here for vertex B. So V will be B. But when we check whether B is visited or not, we see V is already visited in this array. So we will not do anything else for the B. V will be here. Similarly, we will not do anything for C. We will not do anything for D. So what is the purpose of this for loop? If you have a connected graph like this, when you start for the first node and go to the algorithm 2 will finish processing all the nodes that are connected to A. If you have a graph, let's say another node E here, F here, at that time, when you finish A, B, C, D, you will process all the vertex A, B, C, D, but you will not process E and F. This for loop will first go through E and go to the algorithm 2. So what the algorithm 2 will do? Algorithm 2 will process all the nodes that are connected to E. That means you will finish here. If you remember, we talked about the connected component. You can find out using the BFS algorithm 1 and algorithm 2 how many connected components are there. In this case, there are two connected components. So how would you know how many connected components are there? You can count how many times this line 7 is executed. The number of times the line 7 is executed is the number of connected components for that graph. Now that we have seen a smaller example of the simulation, let's go through another example with a bigger graph. Couple of things to remember for this simulation. We need to keep track of time. When a vertex was first visited, we need to keep track of Q. Q will keep track of which vertex to visit next. And again, we need to keep track of which vertex are already visited. It is easy to keep track of the visited here in this simulation, but in actual computer programming, you might want to create an array for all the vertex. Okay, let's start the simulation. So if the start vertex is not given, you can start alphabetically. So I will start from A. What I do, I visit A, I add A to the queue and keep track of time when A was first visited. In the computer programming, what you have to do, in the visited array you created, all the entry will be false at the beginning, right? So when you visit A, what do you have to do? You have to make this to true. Okay, next step. What are the adjacent vertex of A? The adjacent vertex of A are B and D. We will always visit or discover any adjacent vertex alphabetically, not in a random manner. So we will discover or visit B and add that to the queue. We visited or discovered B at time 1. Next, we visit the vertex D and the time for the visiting of that vertex is 2. Before adding B and D, we have to DQA. Okay, what is the next step? Next step is looking into the queue. We see queue is not empty, so we will DQ B from the queue and take a look at what is the adjacent vertex of B. The adjacent vertex of B or C will be visited at time 3 and E that will be visited at time 4. So we have done all the adjacent vertex for B. Again, take a look at Q. The queue is not empty, so we will DQ D. For D, what are the adjacent vertex? The adjacent vertex are B and E. As we have already circled B and E, that means we have already visited B and E. That means if we check this array, we should find the entry for B and E true. So we don't have to do anything else. Again, let's check at the Q. Q is not empty, so DQ C. For C, there is no adjacent vertex because there is no edge outgoing from C. So we don't have to add anything to the Q. Again, Q is not empty. We take a look at E. We NQ E and take a look at all the adjacent vertex of E. The adjacent vertex of E are F, which is discovered at time 5, and G, which is discovered at time 6. We are done with E. Let's take a look at the Q again. Q is not empty, so we will DQ F. For F, we have two vertex G and I. As we have already circled G, that means we have visited G. We will not visit G again. we will visit I. I will be visited at time 7. We are done with F. We take a look at the Q again. Q is not empty, so we will DQ G. What are the adjacent vertex of G? We have only one vertex, which is H. That means H will be discovered at time 8. Next, there is no other adjacent vertex, so we are done with G. We take a look at the Q. We see Q is not empty. We DQ I. What are the adjacent vertex of I? Adjacent vertex of I are D and H, but they are already circled. That means they are already visited. We don't have to do anything else. Next, we take a look at the Q. Q is not empty. We DQ H from the Q. And what are the adjacent vertex of H? Only adjacent vertex of H is F, which is already visited, so we will have nothing to do. At this time, every vertex of the Q has DQ'd. So Q is empty. That means we have finished processing all the vertices. So this is what a simulation of a BFS look like. And you should practice this one in some other graph so that you can get hold of the simulation. You should expect some simulation of BFS in the exam.